So this is part 2 of the chemistry chapter, chapter 2. The first part was done in class. So when we look at chemistry, at the molecules of chemical reactions, basically we can divide it into two groups. There's the inorganic compounds and the organic compounds. The difference between the organic compounds and the inorganic is all organic compounds contain carbon. And it's as simple as that. If it has carbon in it, it's an organic compound. There's a few minor exceptions to that rule, but they won't impact us in physiology. The inorganic compounds are all of the rest of the compounds that don't include water. So organic doesn't mean grown without pesticides. It means contains carbon. The inorganic compounds doesn't mean that they aren't essential for life. It's just that they don't contain carbon. So the inorganic ones that are essential for life are the various salts, water, acids, base, etc. The organic compounds are really carbohydrates, fats, proteins, nucleic acids are the ones that we care the most about in physiology. So water makes up 60 to 80% of cells. The cytoplasm of cells is mostly wet. All the chemistry of physiology is aqueous chemistry. It's got to do with water. So water is very important compound that's in the body, H2O. It's hugely important. We have a whole chapter devoted to water balance. But we have to look at kind of the properties of water. So there's a bunch of properties of water that really help define how the body works. So one of the very first ones, we'll just do it in the order that Mariup has chosen, is the high heat capacity. So what this means is that there's a lot of energy can be absorbed into water and released from water without changing the temperature very much. You all know this. So on the 24th of May, you go down to the beach. It's 30 degrees outside. The sand on the beach is so hot that it burns your feet. But you can't go into Lake Simcoe because the water's too freaking cold. So the land and the air have heated up way sooner than the water heats up. And that's because it takes an awful lot of energy to actually change the temperature of water. Conversely, you can go swimming right now in Lake Simcoe, and the weather can be quite cold, but the water temperature stays about the same. What this means is that since our bodies are mostly water, we can run out to the car in January across the parking lot and not freeze solid. Our core temperature doesn't change. The reason that our body temperature is held so constant is because of the amount of water that's in us. You know this. You put a pot of water on the stove, and you can still stick your finger in it 2 minutes after you've turned on the burner, because it takes a lot of energy to actually bring that water, change the temperature, bring it up to boil. So related to that is something called the high heat of vaporization, which means that for water to actually change states and move from liquid water to gaseous, to water vapor, requires a huge amount of heat, even more than the temperature change. So what it means is a very little bit of water vaporizing can cool a very large mass. Around my swimming pool, I have stones, patio stones sort of thing, and those things are heavy. It took me a lot to lay those things. It almost takes two guys to carry it. So each stone probably weighs 90 to 100 pounds. Like they're big, heavy stones. They're a couple of inches thick, and slate. Now they get really hot because they're dark colored. The sun gets those stones so hot you can barely walk on them. But if you take a handful of water, just like not even, less than a cup of water, and you throw it on the stone, that couple of ounces of water will cool a 100-pound stone tremendously. Very little water absorbs all that heat out of that stone to turn into water vapor, to evaporate. And so this is a very useful cooling mechanism. I find it an interesting thing, and I'll throw this up for you. Do you know those sponge can cozies that you get? You put them around your beer. They're made out of sponge. A lot of people use them. Everybody uses them incorrectly. It's not to be insulation. It's not supposed to be to keep your hands from touching the cold can. What's supposed to happen with those is you're supposed to get them wet. When you get the sponge wet and you put the can of beer in it, the water evaporating out of the sponge will actually cool your beer. You can get your beer cold without a refrigerator by evaporating the water out of the sponge that surrounds it. When you have a canteen, camping canteens all have that carpet on the outside. The idea is that you get that carpet wet when you're filling the canteen, and the evaporation out of the carpet will actually cool the water that's in the canteen. Similarly, it doesn't take a lot of water out onto our skin in the form of sweat to cool our bodies down and help maintain temperature. Water is a polar compound, and so is therefore a very good polar solvent. So it causes dissociation of any ionic bonds. They come apart in the presence of water, and those substances end up dissolving. So it is the polar properties that allow colloids to form, right? And because it's a good solvent, it's the major transport medium to move stuff around your body. So that's how we get sugars around the body. That's how we get vitamins. That's how we get oxygen and such. So the solvent properties are huge. So you look at it, and I talked about this in class with the slightly negative side and the slightly positive side over here, and how the hydrogen bonds form. Water is very reactive, so we use a lot of oxygen, we use a lot of hydrogen in our body, and the source of that hydrogen and oxygen is water, the H2O. So we call breaking things apart by inserting water molecules in it. So when peptide bonds of a protein are broken, digested really, into the associated amino acids, we call that hydrolysis, because we add an OH to one side and an H to the other. Hydrolysis, to break apart using water. We build things like making glycogen, making compounds, like any of the anabolic compound making in our body is done by removing water from the constituents and having them stick together because of that removal of water, and that's called dehydration synthesis, putting together things by removing water. Cushioning is another big thing. So, it's the typical water bed. It's probably a good thing if you've got a lot of interstitial fluid at places that rub. You see that at inappropriate rubs. That's what a blister is. It's an attempt to protect the tissues by inserting a cushioning of water. We see it in bursa at joints. We see it in the cerebrospinal fluid, protecting and cushioning the brain and spinal cord. So it's an important property of water. Another important inorganic compound are salts. Now, anything that's held together with ionic bonds and will dissociate in water. Now, there's basically three different classes of compounds that are held together by ionic bonds. One contains hydrogen ions, so things like H plus Cl minus is hydrochloric acid. Anything with that H plus as the cation is considered an acid. Anything with the anion being OH, which is called hydroxyl, OH minus, so NaOH minus, which is sodium hydroxide, is called a base. It's alkaline. All other things are called salts. And when salts are associated, they are a salt. When you put them in water, they dissociate into ions. And ions are electrically charged, so we call them electrolytes. And we use them to conduct electrical currents in any solution. So all nerve functioning and all of that, all muscle contraction, rely on the salts. And the salt that's really the most important one is sodium. Although potassium, calcium, iron, magnesium, and a bunch of the other ones are really important. Now, we tend to talk in physiology about the cations, the positive charged ions, sodium, potassium, calcium, magnesium, iron, those ones. And we tend to talk less about the anions, the chlorine, the hydroxyls, the phosphates, and those sorts of things. But the salts that come together are the anions and the cations together. And as we use them, we'll talk more about the specifics. So acids and bases are electrolytes, and they have hydrogen ions or hydroxyl ions. So acids release hydrogen ions into the solution. The more that the hydrogen ions are released into the solution, the stronger the acid. Bases accept protons. So sodium hydroxide becomes sodium and OH, and then OH grabs hold of an H and becomes H2O. So bicarbonate ammonia are important bases in the body because what they do, they don't have an OH, but they readily accept a hydrogen ion. So HCO3 minus will bind with any available H plus to make H2CO3, so that bicarbonate becomes carbonic acid, and then the carbonic acid, HCO3, turns into H2O and CO2, water and carbon dioxide. Very important reaction in the body. Ammonia is another one that's very important, and it turns into urea, and we'll see later why it works. We'll do a whole chapter on acid-base, so I'm not going to spend any time on it right now, right? And the concentrations and pH I will do at a later time. And so all of this is an introduction to that, but I would rather deal with it when we're dealing with acid-base homeostasis and buffering, etc. The organic compounds are all made by dehydration synthesis, and they're all broken down by hydrolysis. All of digestion is hydrolysis. And So this is an example of how this works. So we take this, so this might be a glucose molecule, and this might be another glucose molecule, and we take an H and an OH from here, and we end up linking them together covalently to make sucrose. So that's dehydration synthesis, putting it together by taking away water. You eat the sucrose, and in your stomach, because of amylase, we break this by adding water down into the glucose and fructose. So this is how this is written. So making it come together is dehydration synthesis, breaking it apart with water, hydrolysis. Carbohydrates are really interesting things. They all have the chemical formula CH2O. So it might be C5H10O5 or C6H12O6. Glucose is C6H12O6. That's why they're called carbohydrates, because what they have is carbon and water as their constituents. They really are the sugars and the starches. If they're not linked together, each ring of the carbohydrate, C6H12O6 or C5H10O5, which would be ribose, those things are called monosaccharides. If we link them together like this monosaccharide glucose and this monosaccharide fructose link together to form a disaccharide called sucrose. Maltose is another, lactose is another. So if you have glucose and galactose joined together, which are two monosaccharides, you get lactose. And it's interesting because there's an enzyme that makes those things come together, and there's an enzyme that splits them apart. If you don't make the enzyme that splits them apart, then you can't break the disaccharide lactose down into the monosaccharides, and you can't absorb it, so it stays in your guts, and so you become lactose intolerant. You can't digest the lactose. You can't cause the hydrolysis of lactose. Polysaccharides are the starches. It's more than one or more than two monosaccharides joined together in a long chain. So glycogen would be a polysaccharide. Cellulose is a polysaccharide. Starches are all that. We use them for cellular fuel. We use them to break apart to release energy. By breaking the bonds between the carbons, we get a lot of energy. Glucose is that major cellular fuel. We also use them structurally for different things. So ribose is in RNA, deoxyribose is in DNA. We use them in various polysaccharide constructions where and on cell membranes and things like that. So, but most of them the most important thing is cellular fuel. So the simple sugars are those, I just talked about it. So here's glucose, fructose, galactose, ribose, and deoxyribose. These things are all C6H12O6. These ones are 5,10,5. The disaccharides are double, so they go together. So glucose and fructose together make sucrose, glucose and glucose together make maltose, galactose and glucose together make lactose. So, yeah. And this would be malt sugar. So this is what they make beer out of. Polysaccharides are starches and glycogen. and they end up looking like these long chains of monosaccharides. Lipids are fats, and they contain all different types of compounds. They all have carbon, hydrogen, and oxygen. Sometimes they have some phosphorus, but not necessarily. So they're all insoluble in water because they are non-polar. They don't have a positive and negative end to them. And there's basically a few types. The most common fat, and the fat that we think of when we think of fat, is called a triglyceride. It's a neutral fat. A fat that's very important for cell membranes, which we will talk about next week, are phospholipids, and they have phosphate in it, so they have fats with phosphates. And what's interesting about phospholipids is the one end of the is neutral, and the other end is actually polar, so they have a polar head and non-polar tail. So the head actually likes water, hydrophilic, and the tails dislike water, hydrophobic. Another class is steroids, and we use these as hormones, and the Eicosanoids, which are a fairly minor group that we'll talk about at the appropriate time. So the neutral fats are a great way of storing energy because they contain so many carbons. Triglycerides contain huge numbers of carbons. So the 3 fatty acids, they might have 33 or more carbon atoms in it. So, and if energy is stored in carbon-carbon bonds, the more carbon atoms there are in a molecule, the more energy that's stored. So that's why fats are so high in calories. There's a huge energy storage. We also use them for insulation. We use them for protection. Like your kidneys are surrounded by a layer of fat so that it holds them in position and acts as a shock absorber. The fat pads on the soles of your feet around your heel are used to protect from when your heel striking, things like that. Fat's also fairly decorative. Breasts are mostly made out of fat. The shape of your face is really because of subcutaneous fat. So a lot of the contours of our body are really maintained by fat. So the triglycerides end up looking like this. You take a glycerol, which is an alcohol with 3 OH groups and 3 carbons, and you add a fatty acid chain here. And the fatty acid, the acid part, is this C double bonded O with an OH, and through dehydration synthesis you make them come together. You end up with 3 water molecules left over when you make fat, and you end up with these. Now, these fatty acid chains, you'll see the dot, dot, dot means that it's more CH2, CH. Right? Now, if all of these fatty acids have got CH2, carbon and 2 hydrogens, bound to another carbon with 2 hydrogens, then every bond is filled, and that type of fat is called a saturated fat. If any of these are CH double bonded to another CH, that means you don't have all the hydrogen at every carbon. There's some double bonds. That's an unsaturated fat. And if that happens multiple times in the fat, it's polyunsaturated fat. So if there's a maximum number of hydrogen, that's the saturated fat. So those would be like animal fats, butter, that kind of thing. Oils tend to be unsaturated. Okay. Now, if we take the triglyceride and we add a phosphorus-containing group at the instead of all 3 fatty acids, so we have 2 fatty acids and a phosphate, we end up with this thing called a phospholipid, and the phospholipid ends up looking like this. So it looks like a fat, and see, this would be an unsaturated one with this phosphate group. You don't have to learn how to reproduce this. Just realize that this end is polar and this end isn't. It's always represented this way because this is trying to escape from those. They try and stay as far away as possible, and the glycerol is what joins them together. As we talk about cell membranes, we'll talk more about this. Steroids are used for hormones, so cholesterol, vitamin D, the steroid hormones. We also use them to digest fats, so we have them in the bile. So this is roughly what they look like, and the only reason that they are fats is because they are non-polar and they're organic. These are really prostaglandins, which are the pain mediators. Preventing the making of these is what Advil does. That's what ibuprofen does. Is it prevents the synthesis of prostaglandins, which is why it's a painkiller, because prostaglandins mediate pain. There are the fat-soluble vitamins, vitamin A, E, and K. Lipoproteins are fats and proteins joined together so that they can transport dietary fats in the blood, and there's various other things. Proteins are chains of amino acids in a very specific order. Now, I'm not going to get too much into this. I think what I'm going to do is talk about proteins in person. So I'm going to, because they're fairly important and they're fairly complicated how it turns out. I can do in 10 minutes with demonstration much more than I can do here. So I'm going to end this video at this point, and we will pick up the rest of this chapter a little later.